Hello, welcome back to the channel. So let's do one more question on calculating indefinite integrals using trigonometric substitution. So again in this question, it may not seem evident to you that this question can be easily solved using trigonometric substitution, but if you'll clearly observe this expression over here, this integral over here, you'll see this quadratic expression over here, right? And whenever we have quadratic expression, we can use the completing the squares approach in order to see or identify a pattern which may be similar to the patterns we saw in the trigonometric substitution cases, right? So now in order to identify a pattern in this question, let's take this quadratic equation out and see if we can do something by completing the squares of this quadratic expression over here. So now you can clearly see that your expression is 4x square minus 12x plus 8, right? And now if you write this expression as simply 4x square minus 12x plus 9 minus 1, you can see that this is a square term over here, right? This is exactly the square of 2x minus 3 whole square, right? When you'll open the square of this term over here, you'll clearly get this expression over here. And now since we have a 2x minus 3 whole square term over here, we can also see the same term over here as well, right? And now in order to simplify our expression, let's use a new function. Let's assume that y is equal to 2x minus 3. So this expression over here, which is also equal to this expression will be easily transformed to y square minus 1, right? And since we also have a 1 by 2x minus 3 whole cube expression in the integral, we can easily convert this 2x minus 3 whole cube into just y cube, right? If we assume our y to be 2x minus 3, right? So now let's write this integral again and see how we can convert this integral into a simpler form over here. So if we write the integral, our integral is basically 1 upon 2x minus 3 whole cube, and then you have square root 4x square minus 12x plus 8, and then a dx over here, right? So now let's first write this expression in this form over here. So if we write our expression in this form, we can easily write this as 2x minus 3 whole cube will remain as it is, and this square root expression can be easily changed to simply 2x minus 3 whole square minus 1, right? So the same expression over here. And now we also have a dx term over here. So if we assume our y to be 2x minus 3, clearly our dy is 2 dx, right? Because the derivative of minus 3 is 0. So dy would be 2 dx. And now let's use this substitution over here to simplify this integral, to further simplify this integral over here. So this integral will become integral 1 upon y cube times square root y square minus 1, and then your dx would be changed to simply dy by 2, right? Because if you shift your 2 in the denominator, your dx will be dy by 2. So dx is dy by 2 over here. And now this integral will be simplified to just calculating the half of the integral of y cube times square root y square minus 1 dy, right? And now in this expression over here, you can clearly identify the same pattern we identified in the trigonometric substitution cases, right? We clearly see an a square plus minus b square x square or a square plus minus b square y square term over here, right? Which gives us an idea that we can easily solve this question using trigonometric substitution. So that is why if you have not watched my previous videos on this concept, I will highly suggest you to first watch those videos in order to get the full idea about how we identified that we'll use trigonometric substitution in order to simplify this integral or in order to calculate the solution to this integral. And you can always find those videos on the I button above, or if you also click on the description, you'll find those videos as well. So now since we identified that we will be using trigonometric substitution over here, the main question is what would we take our y to be? So in this case, you can see a y square minus 1 term, and you also know the relation between secant square theta and tan square theta, which is, you know that secant square theta is 1 plus tan square theta. So secant square theta minus 1 is tan square theta, right? So that is why in this case, if we'll take our y to be secant theta, this term will become secant square theta minus 1, right? which can be easily transformed to tan square theta, and then when it will be transformed to tan square theta, we can easily simplify this square root expression over here as well, right? So that is why let's take y to be secant theta and see if we can simplify our integral further. So now let's take our y to be secant theta. If we take our y to be secant theta, we know that dy is basically secant theta tan theta d theta. So now this expression over here will be changed to 1/2 of the integral 1 upon y cube. So y cube is secant cube theta, and then under root y square minus 1. So under root secant square theta minus 1 over here. And then your dy will also be changed accordingly to secant theta tan theta d theta, right? So now you can cancel 1 secant theta with 1 secant theta in the denominator, and this secant square theta minus 1 can be easily changed to tan square theta, and taking the square root of tan square theta will get tan theta, right? So this integral will be changed to 1/2 of 1 by secant square theta tan theta times tan theta d theta, right? And now you can cancel this tan theta with this tan theta. We know that secant theta is basically 1 upon cos theta. So this expression will be simplified to just calculating the 1/2 of the integral of cos square theta d theta in this case, right? And now you are already familiar with calculating these type of integrals. You'll use the double angle property of cos theta. And if you find trouble in remembering the double angle formulas for cos theta, I usually follow this approach, which is, as we know that cos square theta plus sin square theta is 1, right? Similarly, if you take cos square theta minus sin square theta, you'll get cos of 2 theta in this case. That is just a way I remembered the cos 2 theta formula by relating it to the cos square theta plus sin square theta expression. And now if you only want the cos square theta in this expression, you can substitute sin square theta as 1 minus cos square theta. And on the other hand, if you want your cos theta expression to be in terms of sin square theta, you can convert this cos square expression into 1 minus sin square, right? And now since we want our expression of cos 2 theta in only terms of cos square theta, so we'll convert this sin square theta into 1 minus cos square theta as well. So this expression will become cos square theta minus 1 minus cos square theta equals cos 2 theta. So cos square theta minus 1 plus cos square theta equals cos 2 theta. This is 2 cos square theta minus 1 equals cos 2 theta. And now we want cos square theta over here, which is 2 cos square theta equals cos 2 theta plus 1. And then cos square theta is basically 1 plus cos 2 theta over 2 in this case, right? And that is the formula you already know about, the relation between cos square theta and cos 2 theta, right? So that is a different approach that you can definitely follow if you want to remember your cos 2 theta expressions easily. So now we have to calculate the half of the integral of cos square theta d theta. Since we have to calculate the half of cos square theta d theta, this can be changed to calculating the integral of 1 plus cos 2 theta by 2 d theta, right? So now this would be 1 by 4 times 1 plus cos 2 theta d theta. And we already know the integrals for both of them. The integral of 1 is theta. The integral of cos 2 theta is sin 2 theta over 2, right? And then you'll add the constant of integration as well, because you got rid of the indefinite integral over here. So now you have your answer in terms of theta, but we want our original answer to be in terms of x, right? Over here, right? So since we did two transformations over here, one from x to y and then from y to theta, we'll have to revert all those transformations back, right? So we'll change our transformation from theta to y and then from y to x in this case to calculate our final answer. So now since we know that our y is secant theta, so if you take arcsecant on both sides, you can easily calculate your theta to be arcsecant of y, or simply secant inverse y, right? So this is an expression for your theta because you want a theta as well. And now since you want sine of 2 theta as well, in order to calculate that, we know that y is secant theta. So y is 1 over cos theta. Cos theta is 1 over y. And now you can simply construct a right angle triangle just like we did in the last videos. If you assume this angle to be theta, you know that cos theta is base upon hypotenuse, right? So base is 1, hypotenuse is y. If you want to calculate this side, it will be easily the square root of y square minus 1 using Pythagoras theorem, right? So cos theta is 1 over y. And now since you need sine of 2 theta, sine of 2 theta is basically 2 sine theta cos theta, right? So sine of 2 theta is 2 sine theta cos theta, and sine theta, as we know, is perpendicular upon hypotenuse. So perpendicular is this one, hypotenuse is this one, which would be root y square minus 1 upon y times cos theta that we already knew is 1 by y, right? So this expression will be simplified to twice of square root y square minus 1 upon y square. So this is an expression for sine of 2 theta in this case. So you got the expression for sine of 2 theta, you also got the expression for theta. Now you can easily solve for this answer over here, right? And the answer you'll get will be in terms of y. So we'll have to do one more conversion from y to x in this case. But first, let's write this answer in terms of y over here. So this would be 1 by 4. Theta is basically secant inverse y. So secant inverse y plus sine 2 theta by 2. So sine 2 theta by 2, which would be the half of this expression. So we can get rid of the 2, right? In sine 2 theta by 2 expression. Because if you take this 2 to the other side, you'll get sine 2 theta by 2, which would be equal to this expression over here, right? So sine 2 theta by 2 is root y square minus 1 upon y square and plus the constant of integration. And now, since you know that your y is equal to 2x minus 3, if you want to calculate the final answer, you know that your y is 2x minus 3. So your final answer will be 1 by 4 secant inverse 2x minus 3 plus under root 2x minus 3 whole square minus 1 upon y. Y is again 2x minus 3 whole square bracket and then at the end the constant of integration, right? So this is your final answer to the integral of your original expression, this one, right? I know this was a complicated question, but it was only complicated due to the calculations we had to do. The approach to solve this question wasn't complicated, right? So that is why whenever you have these type of expressions, when you have a quadratic equation, always try to simplify your quadratic expression by using the completing the squares approach, and then see if you can identify a pattern which will convince you to use trigonometric substitution in order to simplify your integrals in these type of questions. So that's it for this video. Again, feel free to comment down in this video if you have any doubts. Follow the channel in order to get notified about the other videos that I'll be uploading. Stay tuned. Thank you so much for watching. Bye bye. Take care.